Now what Minkowski's theorem does is gives us conditions that guarantee a set contains one of these non-zero lattice points. And the conditions are really intuitive. Just consider pouring batter evenly on top of a hot plate. If we start pouring batter at the center such that it fills out evenly, and the amount of batter we pour is large enough, we are guaranteed that the batter overfills. Minkowski's theorem captures the same idea. Just think of it as a form of pigeonhole principle, but for lattices. The first condition of Minkowski's theorem is that our set X needs to be centrally symmetric, or symmetric with respect to the origin. Formally, for every x in X, minus x is also an x. The second condition is that our set needs to be convex. For every x and y, all points on a line connecting x and y must also lie in the set. Precisely, for every x and y in X and t in 0, 1, x plus t times y minus x lies in X. Note that a set satisfying central symmetry and convexity is going to force our set to contain the origin. This is easy to see. For any x in our set, minus x is also in our set. So by convexity, x plus 1/2 of minus x, which is just the same thing as 0, is also in the set. So like the batter, we can visualize our shape as growing outwards from the origin. The last condition is the amount of batter, or the size of our set. First, notice that we can use our lattice to break up our space into congruent regions. The last condition is that the volume of X is greater than the combined volumes of 2 to the n of these regions, where n is the dimension of the space. The 2n condition may seem scary, but it's really intuitive once you think about it. Let's just take a look at case n equals 1, 2, and 3. On the real number line, to guarantee our set contains a lattice point, we need our set to fill the first two regions of our lattice. In R2, for our set to start overflowing, it needs to be greater in volume than the 4 center regions. And in 3 dimensions, the space needs to be greater than the 8 center regions. From these diagrams